Okay, hello. So we start today's lesson. We continue graph theory. So I start with some very simple examples. So if you remember, let me just remind you about what we did before. We talked about the isomorphism in graphs. I just want you to know about that. Then we started talking about the degree of a vertex. Degree of the vertex is the number of edges incident with that vertex. Yes. And then we also talked about some terminologies. Odd vertex means a vertex whose degree is an odd number. An even vertex. Similarly, isolated vertex is a vertex whose degree is 0. And pendant or leaf is a vertex whose degree is 1. And I told you that what is the main important thing to remember is about the loop, yes? So if you have a loop, if I ask you what is the degree of C, you do not count, because there are two edges, of course, technically incident with C, but you don't say the degree of C is 2 by definition, you count each loop twice. So if I ask you what is the degree of this, you draw a very small circle around that, and then you see that you have 3 edges involved there. So it's from this perspective, it is very natural to say that each loop can be counted 2 times when it comes to degrees of the vertices. Yes? Okay, so this graph theory is mainly you need to work on yourself. So you see that it is not very a classic way. We don't have a very structured way to introduce these things. So you need to play around with these examples to get more familiar with the concept of a simple graph or multigraph in general graph theory. Okay, so by the way, do you remember these notations? Capital delta and a small delta, what were they? Yeah, this capital delta is the maximum degree that you can see in the sequence of degrees, and this little delta is the smallest degree. Yes? Okay, now, for example, I'm asking you here, draw a simple graph of part 1, order 5. What was order? Do you remember? These are crucial things. There are many words that you need to remember. Order is the number of points or vertices, and size is the number of edges. Yes? So here I'm asking you to draw a simple graph whose order is 5, size is 7, delta, capital delta is 4. Yeah? You can also do it yourself. I don't think that's a hard problem. So I see that the order is 5, so it means that I need to put 5 points here. So this is 5 points. And then I want to have 7 edges, but I want to have delta equals to 4. When you say delta equals to 4, it means that at least one of these vertices has degree 4. So it doesn't matter which one I choose. So let me choose this one. This is first degree of that. This is the second one, and this is the third one. Yes, and this is the fourth one. So it means that I have, by the way, this kind of vertices is called a full. I don't want to disturb you with a lot of words, but that is called a full vertex. It's connected to every other vertex. Okay, so when you say I have size 5 and delta is supposed to be 4, it means that at least I have a full size, a full vertex. For example, let us consider this to be full. So far, this condition is met. This condition is also met. So I have to have 7 edges. So far, I have 4 of them. But I need to draw it in a way that I do not spoil this. Okay, of course I cannot do anything more than that. So I don't know. I hope that you agree with me. This is one possibility. Yes, I forgot to turn off this feature every time. Anyway, yes. So is that okay? Do you agree? This is one of those. I don't know. Have you come up with a different answer or what? Do you think that this is the only one we can do? Yeah, for example, instead of drawing this one, let us drop this one and draw this one. Is that also okay? So that's also okay, but be careful. 1, 2, 3, yes. So we have only 3 of them. So that's also okay. So instead of that one, you can draw this one. So this is one of the possibilities, yes? Number 2. Number 2, we want to do the same thing. Order is 5, size is 7, but minimum degree is 1. So what should I do? First of all, I put 5 points, yes. I need 5 vertices. And delta is 1. So decide about one of them. So for example, let us consider this. I want to make delta equal to 1 here. Okay. Of course, you can have more than one delta equal to 1, but this is at least one of them. Okay, I need 6 more edges. How do you think I should do that? So it is important not to touch this one. If you want to keep the degree of this one 1, which you have to because delta is 1, it means that at least there should be one pendant or one leaf in the graph. Okay, so what can I do? Do you have any suggestions for me? How many more edges I need? I need 6 more edges. Yes?
We can connect the other point, which we've drawn out the line.
Yeah, so it means yes, every other ones. Yes, so I would say that let us consider this. Yes, and then let me consider this, and let me consider this. Do you agree with me now? Yes. If I ask you what is the order, you would say 1, 2, 3, 4, 5. So I'm respecting this. If I ask you what is the size, 1, 2, 3, 4, 5, 6, and 7. So I'm also respecting that. And if I ask you what is the minimum degree, you see because of this one vertex, the minimum degree is 1. So by this drawing, I am respecting all the conditions, so that's completely okay. And this is something that you need to know. You will get some questions like that in the exam, and they are not hard. Okay, let us go to the next example. Is there any simple graph? By the way, what is the difference between simple graph and multigraph? I'm just reminding you about these things. What's the difference? Yes, Carl?
Simple graphs don't have any loops and multiple edges.
Multiple edges, yes? So I'm not allowed to have any loop or multiple edges. Okay, so is there any simple graph of order 10? By the way, what was this notation we use for order? P. What is the size 5? With exactly 5 isolated vertices such that capital delta is 5. Is it possible to draw such a graph? So when you are thinking, I'm just completing. I have 10 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want to have exactly 5 isolated vertices. So you need to choose 5 of them. So it doesn't matter. Yeah, 1, 2, 3, 4, 5. So let us consider these. So if you don't mind, let me change the color of these 5. 1, 2, 3, 4, 5. I am not allowed to touch them if I want to have exactly 5 isolated edges. Vertices. Okay, so now answer me. Is it possible to have a graph of with these properties? If yes, you have to draw it. If not, you need to motivate. Why not? Yes?
It's not possible.
Can you elaborate more?
If we try to connect all the grade, if we choose one of the
Great
grade
ones.
dots and connect it to all other grade dots, then it will.
At most 4.
Yeah.
Exactly. Thank you. Because you say that the maximum degree should be 5. So it means that I should have at least one vertex with degree 5. So it means, for example, if I want to make this degree 5, I have to connect this one, 1 degree, 2nd degree, 3rd degree, 4th degree. Okay? But because I'm not allowed to have multiple edges, what can I do for making it to be 5? I have to connect this with one of these purple ones. But if I do that, then I will not have 5 isolated vertices. So by this argument, it is clear it's not possible. Is that clear? The questions are very simple, but I've designed them to learn these terminologies mainly, not something very interesting. So I would say no. I don't want to spend time on it. Not possible, yes? Okay. This is a very nice problem. I want you to think a little bit about that. This tells you that let G be a simple graph of order greater than 1. Show that there are at least two vertices in G whose degrees are equal. Is this statement also true for a multigraph? Now, first, forget about the second part. So it is very interesting. It doesn't matter how you draw your simple graph. If you find the vertices, if you find the degree of all vertices, at least two numbers are the same in this list. You want to argue for that. Is the question clear? Yes? So for example, here, if I just go back to the other graph, okay, that is unfortunately a multi-graph here. I don't have any other graphs here. So yes, for example, here, let us consider this case. This is a simple graph. Let us write the degrees. What is the degree of this one is 1. What is the degree of B is 3. What is the degree of C is again 3. The E is 3. D is 2. You see, of course, 3 has been repeated 3 times. It is not possible to draw a graph so that when you list the degrees, no number is repeated. At least one number should be repeated 2 times. We want to argue for that. And you have infinitely many degrees of freedom because there are infinitely many simple graphs out there. You want to find an argument for all of them. All of them. Do you have any idea? Do you feel the type of this problem? It is a little bit familiar from one of the previous topics. Can you name that topic? Yes?
It was the whole thing about the pigeon.
Pigeonhole principle. Yeah, it's clear. I don't know. It's not hard to feel there is a connection between this kind of question and that pigeonhole principle that we had before. Okay, but how do you argue for that? So I say that let G be a simple graph of order P. Can you tell me what are the possible values for degrees in general? For example, let me consider a graph of order 5, only 5 vertices. Is it possible to have a degree 0 somehow? Yes, I do not connect one of the points to anything. Can I have degree 1? It is possible to imagine, yes, I can also have degree 1, 2, 3, 4. Can I have degree 5? No. So you see there is a limitation because what is the meaning of degree 4? It means that I connect one of them to every 4 other 4s. But if I want to have a degree 5, it is not possible. I do not have enough room. I have only 5 points. Even if I connect these to all of them, the maximum degree becomes 4. If I want to make the maximum degree 5, I have to have a multi-edge, which is actually not allowed. So now can you tell me what are the possible numbers for degrees if I have a degree P graph, simple graph? What would be in my list in general? Yeah?
Q is
No, forget about Q. I'm just talking about degrees. Assume that you have a simple graph of order P. What are the possible degrees that you might face with? Yes? 0, 1, 2, up to P minus 1. Agree? These are the only possibilities that I can have. Okay? In that case, so the possible degrees of the vertices are 0, 1, 2, 3, 4 up to P minus 1. Is that understandable? 0 is easy for you to understand, I would say. But do you understand why the maximum value is p minus 1? Yes, because at the most, if I want to make it full, I can only connect this to all other vertices. So it becomes p minus 1 edges. P minus 1 edges, yes. Okay. But the problem is this. Can I directly use the pigeonhole principle here? Because I can consider the vertices as the pigeons. I can consider these as pigeonholes. Yes? I will take the first vertex, read its degree. If its degree is 0, I put it in the first pigeonhole. If its degree is 1, I put it in this one. If it is 2, I put it here. Yes? So this is the way that I want to put these vertices here. But unfortunately, if I ask you how many pigeonholes do you have? How many pigeonholes do you see here?
P minus 1.
No, be careful. P, because 0 is also there. From 1 to p minus 1, there are p minus 1, but you also have 0. So in total, you have p pigeonholes. How many pigeons do you have? Unfortunately, exactly p. Do you understand what's going on? I have p vertices. I want to give the role of pigeons to the vertices, and I want to give the role of pigeonholes to these numbers. The numbers that you see in this list is p, and the number of vertices is also p. So if you are completely unlucky, might be the first pigeon goes into this room, the second pigeon goes here, the third goes here, and the last goes here, and it means that this is not possible to have one of them repeated. But do you think that something like this can happen in practice? Can you say why no?
Because there are more pigeons.
No, there are no more pigeons. There are p pigeons, and there are p pigeonholes.
It's P minus 1.
No, this is not p minus 1. I told you, this is p. It is from 0 to p minus 1, yes? From 1 to p minus 1 is p minus 1, I agree, but there is also 1, 0 here. Yes, Carl?
It can't happen in practice because 0 and P minus 1 can't occur simultaneously.
Exactly. You see, because when you say that I have a p minus 1, a full vertex, what does it mean? It means that I am connecting that vertex to every other vertex. So there is no room for isolated vertex. Is that understandable or not? And if you have an isolated vertex, there is no room for a full vertex. So even though in principle we have p pigeonholes, but in practice there are p minus 1 pigeonholes, yes? Because the first one and the last one cannot happen simultaneously. So I would say I don't want to write it down. I want just to talk it orally. So it means that if you think about a simple graph that has an isolated vertex, then you don't need to consider this. You can consider up to p minus 2 at most. So there are p minus 1 pigeonholes. Or if you have a full vertex, then you will not have this situation. Again, you have p number of vertices. Sorry, p minus 1 number of vertices. So it is completely clear in this case, there are two pigeons that have to go into the same pigeonhole. Is that understandable or not? Everyone, yes? Happy or not? Yes or no?
Yes.
I don't think that you are very happy about the argument. Are you, Jessica? Yes? Martinez? Megan? Max? Are you happy? Yes? Okay. But what do you think about the multigraph? Do you think that this idea is also correct in the multigraph? If yes, you need to prove it. If not, draw a picture for me. Yes?
My counter example would be a graph order of 2.
Let me draw it. So you are giving a counter example for me. So you are saying that order 2 points.
Yes, and then okay, the simplest one would just be one of the vertices connect to themselves.
Okay, a loop here. Okay. Now if I ask you what is the degree here? 2. What's the degree here? 0. No repeated. Yes. So if I want to let room for multigraphs, this theorem is not correct. Okay, but let me ask you another question. You just go to you are looking a party from outside, and you want to say that there are at least two people have the same number of friends in that party, even if you don't know the people. Yes. So, for example, assume that you are a bird, you are seeing a party from outside. What you can see, you are a mathematician bird, of course. And then you will say that there are two people, even if I don't know any of them and I don't care about them, because probably these are humans, they are oppressing us. But anyway, there are two people there, definitely, or it might be more. There are two people there having the same number of friends, assuming that friendship is a uh, mutual relationship. Let everyone thinks about it. What I want you to think about, is there any connection with this problem that I just expressed and this first part of this problem? Yes, Alex, that's your turn because this
I
stuff.
have one question and then an answer.
Okay.
Allowed to be friends with people outside of the party?
No, no, no. In that party.
Yeah,
So might
it's
be I did it wrong. There are two people at least in that party that have the same number of friends in the same party. Yes,
then
thank you very much.
then it would be yes, there is at least
So how can you cook up the argument now?
because
Is there any relation between this apparently totally different problem and this abstract graph problem here? Yes,
my
you
problem
yourself.
is
Yeah,
people usually aren't friends with themselves, so
yeah.
it's a simple graph, and then I put other people as
Probably
friends.
the best friend of yours is yourself, aren't you?
That wouldn't count.
Probably you are the only person who care about yourself mostly. Yes, most of the time. Yes. Yeah. Anyway, just this.
Yeah,
Yeah.
and then the edges are the friendships.
Exactly. So what you say, assume that I have in that party, assume that there are p people. So what we do, we associate a point in my imagination to each one of those people. Yes? And then I connect every two person which have this friendship relationship. Yes, do you agree? For example, if A and B are friends, I put a line between them. If A and C are not friends, I don't put a line between them. So by looking at this graph, that's the friendship graph. So immediately you can realize. But at the end, do you agree that this would be a simple graph? Because if you follow the rule, first of all, you will not have a loop because we are not considering friendship with ourselves, I'm considering friendship with others, and we will not have multi-edges because I do not want to emphasize that, okay, A, 100% I swear A is friend with B, yes? Well, I just say A is friend with B. So what I'm saying is at the end of the day, what you get is a simple graph. The friendship graph is a simple graph. Now, if I ask you how many friends this guy have, in abstract notation, what I am asking about, I'm caring about the number of friends of A. It means that I am counting what? The degree of A. Do you agree? So the number of friends that A has is the degree of A. The number of friends B has is the degree of B. Do you agree? And we just showed that there are at least two vertices with the same degree. It means that there are two people with the same number of friends. Is that understandable? So might be if I stated this problem in this way, you didn't find the connection between graph theory and this problem. But I hope that you agree that this way of thinking was much easier to tackle this problem. Yes?
Probably that's also a very boring party.
Why? Because of that, you mean?
Yeah, maybe of course.
Yeah. But of course, parties are for making
Yeah,
friendships usually. Yes. Yeah.
it's a good party.
Yeah. So that's a but of course that would be a dynamic graph. Yes, it is growing by time. Anyway, but do you understand this connection? I really enjoyed this problem first when I was actually hearing it for the first time. So this is a different connect. This is a different problem, apparently a different problem. So that is extremely important, especially in computer science and discrete mathematics, to find abstract problems which are equivalent to real world problems. It's extremely important skill that if you want to be a good coder, you need to appreciate that. Okay, so there is another problem in the book. It is a level 3 problem. but it is extremely important. I want to state it as a theorem, and I want you to know about that. It is one of the level 3 problems in the book. That is something about the sum of all degrees. Okay, so yeah, we can just, and the good point is that it is also true for multigraphs. Both for simple and multigraphs, this theorem is true. This tells you that if you add up all the degrees of all vertices, it's a very nice thing. It becomes 2 times the number of edges. Yes, if you add all degrees, what you get at the end is 2 times the size of the graph, even if the graph is multigraph. So for example, before trying to understand this problem, I told you that you need to understand how to solve it. It's a level 3 problem in the book. But let us, for example, go to the graph that we had before in the previous session. If you see on this, I have already determined all the degrees of all the vertices here. So let me start adding them up. 3 plus 4, 7 plus 3, 10, 11, 11, 13, 14. Yes? So if I add them up, it is 14. Now let me count the number of edges. So how many edges are there? I have already calculated actually, but let us count it once more. 1, 2, 3, 4, 5, 6, and 7. So the size is 7. And if you double 7, it becomes 14. And 14 was exactly the number that I got by adding the degrees of vertices. Is that understandable? Okay, but how do you cook up the argument now? Oh, sorry, I'm going in the wrong direction. So how can you cook up this argument, which is a problem in the book? Intuitively, it is very clear. Can you see the argument? It might be it's better to put the graph in front of your eyes. Might be you can understand what's going on. Yes, Lube?
For every inch we add 2 degrees.
Yeah, no, but I want to have a little bit more precise. I would say the other way around. So for each, so when you count the degree of B, what you are doing, you are counting the number of edges connected to B. Okay? So when I count the degree of B, I'm counting these two. But because of each edge is connected to 2 vertices, for example, when I come to F, I am counting this edge once more. Is that understandable? So when I say the degree of B is 4, I am counting this edge, this edge, this edge, and that edge. Do you agree? But when I go to F, I count this one again. Yes? Do you understand? So if you continue, for example, if I go to G, I will count this one again. So every edge is being counted 2 times, if that is a normal edge or a multi-edge. And for the loop, that's also clear because loop itself is being counted twice. Yes? So when I go to C, I count this edge 2 times. Is that understandable? So it means that if I have a edge or a multi-edge, I count each of them 2 times. One on one vertex, one on the other vertex. But if I have a loop, because of that convention for the loop, when I am counting the degrees on C, I am counting the loop 2 times. So it means that in total, I am counting all edges 2 times. Is that understandable? Yes or no?
Yes.
Okay. But if you want, we can cook up a nicer argument, which is more rigorous. So it's more abstract, but more rigorous. So let me just introduce you a set. For example, I would say let A be this set. Be the set of E and V's such that E is an edge. So let me see if this is the other way around. Yes, E is an edge, and V is a vertex incident with edge, incident with E, incident with E. So let me try to describe what I mean. What I mean here, I put ordered pairs inside this set. How? The first component is any edge that you like in your graph. But when you want to put a vertex, you put a vertex which is on that edge. Is that understandable? So this is the way that I introduce UA. Now I want to count the number of elements in A in two different ways. And then if I do the calculations correct, then it means that these two values should be exactly the same. Yes? Okay. Now, can you tell me how can I count by combinatorics? How can I count the number of elements in A? Can you tell me how many, so you see that if I have two, I have a task that can be accomplished after I put E here and V here. Can you tell me how many choices I have to have for an edge? How many choices do I have? This is a graph of size Q, and I want to put an edge here. How many options available?
P minus.
No. Be careful. Assume that you have a graph. Your graph has Q edges inside it, and you want to take an edge and put it in as the first component. How many options are available in front of you?
Q.
Just Q, yes? I have Q options available. So if I want to count the number of these ordered pairs, for this one, I have Q options available. Now imagine that you chose one of the edges, and now you want to put a vertex here. How many choices you have for that vertex to put it here? Yes? Two, yes? Either you can put here or that one, yes? Is that understandable? So so you have Q options for E, but for each choice, you have two options here. Do you agree? Is that understandable? I have an ordered pair. The first component is an edge. The second component is a vertex on the edge. How many options are there for choosing an edge? Q. Now you have chosen one of your edges. Now you want to see how many vertices are edges are incident with that edge. One, two. So there are two choices. So in total, can you tell me what is the cardinality of A? What is the cardinality of A? Something is going wrong, yes. This is happening for every classroom, yes. Yeah, I just want to tell you that this is not just you, probably. Every classroom is suffering from this situation. We can call it chronosymptom symptom or something, what I don't know. But can you tell me what's the cardinality? Yes?
2 to the 2 cube.
You are making things hard. Just imagine. So let me tell you once more. Do you see that I want to set up an ordered pair? In the first component, I want to put an edge. In the second component, I want to put a vertex which lies on the edge, on that edge. Is that understandable? Now I am asking you, how many options do I have for the edges? It's Q. There are Q out there. I take one of them and put it here. Now assume that you put your edge there. Now you want to choose a vertex that lies on your edge. How many options are available? Don't think about loops. How many options are available there? Two. Okay? So now I want to count the total number of these ordered pairs. So 2 times Q. Understandable or not? So it is 2 times Q. So this way of counting gives rise to 2 times Q for the number of edges. So for this, the number of elements, the cardinality of this set. But now let me count it in a different way using the sum rule. I want to count the same thing, but this time using the sum rule. Okay, how do I do that? let me consider a vertex. This time, can you tell me how many? So for example, I want to choose a vertex here, okay? And let me choose a vertex number 1, okay? So can you tell me how many ordered pairs are there where this one is V1? Please think, don't spoil the problem, okay? I'm asking you, I am taking one of those vertices. I put that vertex here, V1, and now I am asking you count the number of ordered pairs so that the second component is V1 and the first component is an edge incident with V1. Can you tell me how many of those ordered pairs I have? No. So let me write. So I have V1 here. Yeah, it's very trivial. It is what? V1. Do you agree? I am telling you that put V1 here. This is your V1, and put all the edges that are incident with E1. This is one edge, two edge, three edge. Okay? So how many of them are there? If there are three, it means the degree is 3. If there are 4, it means the degree is 4. Do you understand that? So it means that how many of them are there? There are degree V1 of them in this partition. If I go to the next one, V2, how many ordered pairs do I have there? For the same reason, degree of V2. And then you can continue until the very last VP. How many of them do you have there? Degree of VP. Okay, now if I ask you how many are there in this, you would say the sum. Yes, so the cardinality on the other side, the cardinality is the sum of all these degrees. Is that understandable? So on the one hand, the number of elements, the cardinality is 2q. If I change my counting strategy, the cardinality in the same time is actually equal to this. So this cannot happen unless these two are equal. Is that understandable? It might be a little bit abstract, but I think it's good to understand this. And if you have questions, I don't know how, might be you can see the faucet. Probably the faucet tells you that, okay, every vertex, every edge is incident with two vertices. So might be, but I didn't feel it very nice abstractly. I want to cook up a very abstract algorithm to count that. Okay. So let us continue a little bit here now. So let G be a simple graph of order 5 and size 7. So when I read this, I would write P is equal to 5 and size Q is equal to 7, such that the degree of 4 of its vertices is 3. Okay, so it means that I have 3, 3, 3, and 3 in my list of degrees. Determine the degree of the other vertex. Yeah, it's very simple. Okay, let me not spend time on it. I will give you the second one to solve. If I want to solve this, you see that there are 5 vertices. The degree of 4 of them is given to you. You don't know the degree of the last one, so let me call it x. We don't know the degree of the last one, and we want to find x. Yes, Alex, do you want to say something? How do you say that? We add the degrees, it should be equal to 2 times the size. Yes? So I would start using this theorem. Sigma degree of Vi is equal to 2q. This means that 3 plus 3 plus 3 plus 3 plus that x that I don't know is equal to 2 times 7. And as you said, exactly 12 plus x is equal to 14, and this means that x is equal to 2. So it's very simple actually. By the way, let me ask you something. There is no guarantee there is such a graph. You are solving and finding this degree. You are trusting the person who designed the question. You are actually saying that if you guarantee such a graph exists, then the last one should have degree 2. This is the meaning. But do you think that this graph really exists? In that case, you need to, do you understand what, from theoretical point of view, there is no guarantee that this calculation makes sense. I am trusting the person who designed the question in case myself. I am telling you that if you tell me that such a graph exists, then I will tell you that the last one has degree 2. But can you draw such a graph with these? So how do you draw it?
Well, I know it should be possible because none of the degrees are larger than 5.
No, that's the problem. It's by the way, there is an algorithm called Havel-Hakimi algorithm, and this is not a trivial problem. So if you can find something contradictory, you would say there are no such a graph. But it doesn't mean that if you cannot find a contradiction, it guarantees that you have such a graph. Unless you draw it, or unless you have an if and only if condition. None of them are if and only if conditions. Do you understand what I mean? This tells you that if such a graph exists, this should be the sequence of degrees. It doesn't tell you that this graph indeed exists unless you draw it. Yes, do you want to draw it? Yes, just tell me.
I draw a pentagon.
Okay, so let me just try to follow you. So you are saying that you drew a pentagon, yes? Yes. What?
I connect all the sides. All the vertices.
Like this?
Yep. No. That's too many.
So,
Just 2 on the inside.
okay, 2 inside and this.
Yeah.
This is what you mean, yes?
Yes.
So let us check. What is P5? It's pentagon. What is Q? 5 edges plus 2, that's correct. Let me show what are the degrees. The degree 3, the degree 3, the degree 3, 3 and 2. Yes, you are right. So this is one of those graphs. So this graph indeed exists. Yes? Is that understandable? But before doing that, this is a big if. If you say this is true, your answer is 2. There is no guarantee that this answer is actually correct. Okay, so now I want you to solve this problem yourself. Okay, so let me just wait a little bit for you. So when I read these kinds of questions, let G be a simple graph of order 9. So I would write P is 9 and size is what? 12. Such that the delta is 2, capital delta is 3. Determine the degree of all vertices and draw a diagram for it. So how do you think this will help us? Little delta is 2, capital delta is 3. How do you think that I can use this piece of information here? How can I use this piece of information? How is it relevant? The minimum degree is 2, the maximum degree is 3. Yeah, it is simple, isn't it? It means that, yes? There are only 2 numbers available as degrees, either 2 or 3. But we don't know how many of them are of degree 2 and how many of them are of degree 3. We want to understand that. Okay, so I would say that because delta is 2 and delta is 3, so this means that the only degrees available are 2 and 3. Agree? So we don't know how many of them are 2. So let us assume that the number of degree 2 vertices, let us call it M. The number of degree 3 vertices is N. Okay, how can I set up my equations? Immediately I know that M plus N is what? What is M plus N?
24.
No, M plus N. M is the number of, 9. Do you agree? Yes, M plus N is 9. But how can I use sigma of degree Vi is 2 times Q? Can you tell me what is 2q? It is clear. 2 times 12. What can I write for the left-hand side? Yes, Alex?
2m plus 3n.
Yes, do you agree? 2m plus 3n. Do you agree? Because in my list, I have only 2 and 3 in this sum. How many of them are 2? M of them are 2. So if I add them, it becomes 2m. And how many of them are n? N of them. Sorry, how many of them are 3n of them? So it becomes 3n. So this means that I need to solve this system of equations. So I need to solve this system of equations. M plus n is 9, and 2m plus 3n is 24. So what is n? N becomes how much? 6. M becomes 3. Yes? Understandable? Yes or no? Okay, now we want to draw the graph. If it is not asked you, if it's not demanded in the problem, just leave it. That's the end of the problem. You don't need to feel worry if this is possible or not in the first place. But if they ask you to draw such a graph, you have to draw it as well. So can you imagine how we can draw that? So let me, first of all, how many vertices do I need? Let me change my color. I need 9. So let me put 1, 2, 3, 4, 5, 6, 7, 8, 9. But be careful, you have to respect this delta, and you need to have 12 edges. I found a trick to do that. Yes, what is your opinion about this?
Wouldn't it be more beautiful to move so that the left side only has one vertex and the right side only has two, and then we have the top and the bottom.
No, I mean, the one that came to my mind is not that way. Daniel, sorry, do you want to say something?
You just wanted to participate and see if it.
Okay, yeah.
You're online.
And online as well.
Okay, so I should.
Yeah. So first of all, let me draw a graph. Do you believe in this one or not? One, two, three, four. So what do I put? No, okay, there are 9 of them. Okay, sorry, there are 9 of them. So I want to keep delta to be 2, capital delta to be 3. So yeah, I think it's correct, isn't it? So if I just draw this one, let us see. If I ask you how many vertices do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is respected. How many edges do you see? 1, 2, 3, 4, 5. Unfortunately, this is not correct. Unless I add one more edge here. Okay, if I add one more edge here, then there are 6 here. There are also 6 here. And then I have 12 edges. That's correct. Now, if I ask you what is the minimum degree, what's the minimum degree in my graph? It's 2. What is the maximum degree in my graph? It is 3. Are there any vertices without which all the vertices are 3 or 2, yes? Degrees. So this is correct, I think. Might be you have a better idea, I don't know. I can also hear yours. So let me double check my. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices here. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are correct. If I ask you what is the minimum degree, it is clear. Let me write all the degrees on top of that. The degree of this is 3, 3, 3, and 3. This one is also 3. This one is also 3, 2, 2, 2. So you see that degrees are either 2 or 3. Is that also understandable? And let us see, is it according to our predictions? We predicted that there should be 6 degree 3. Are there 6 degree 3s? Yes. 1, 2, 3, 4, 5, 6. And there should be 3 degree 2. That's also according to prediction. So at least the way that I drew it is correct. But I want you to see if you have another opinion. It means that you need to draw something which is not isomorphic to this if you want to give me another method. Yes?
In my version, I have. I can show you a picture, but
Yeah, I think it's better to draw it if you can. Can you do that? Yeah. I don't know if I have, yes.
This way. But you could also straighten it.
Okay, so, okay. Okay, if you can draw it, I can draw it here. So let me just see. Can you draw it here for me? Yeah, let me just give it here. So let me just try to mimic yours. So what you have, 1, 2, 3, 4, 5, 6, 7, 8, yes?
9.
So you have a 1, 2, 3, 4, 5, 6, 7, 8, okay, and 9. Okay, something like this. Okay, so, and then how should I connect them? Which one is connected to which one? So if I understand you correctly, this is one of them, yes? And the other one is which one? Is this one? Yes? Okay, is that it?
No, one more.
One more from here to here. Okay, so let us check yours. Thank you. So Alexander is actually drawing this graph for us. Let us check. How many edges you see here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. So it is 12. Yes, the size is 12. How many vertices you see? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's also correct. Okay, so let me write the degrees. The degree here is 2, here is 3, here is 3, 3, 2, 3, 3, 3, 2. Yes, exactly. So the minimum is 2, the maximum is 3. And is it according to our predictions? Yes. How many 3s you see? 1, 2, 3, 4, 5, 6. That's correct. How many 2s you see? 1, 2, 3. That's also correct. So I hope that you agree that this graph that Alex actually drew is not isomorphic to what I drew. They are not the same thing. Yes. So at least we see 2 of them. Of course, this is not part of your lesson, but the reason that when I saw Alex's graphs, I asked him to draw it because this graph is one piece. There is a terminology. This is called connected graph. Okay, my graph is called disconnected, but we don't study these things further. Okay, but I just want you to see that at least we were able to draw 2 versions of this one. So we are on the safe side. This graph actually exists. Yes, and this tells you that this is important. If you don't do the calculation, Alex, if you just do this and tell me that, okay, there are 6 degree 3 vertices and 3 degree 2 vertices, I cannot accept it from you because I might say that, have you seen all those graphs with those properties? If you have drawn all of them, yes, I can say that, okay, but the calculation is necessary. The calculation is telling you that if this problem is possible, these are the only possible values, but there is no guarantee that these are possible. By drawing one of them, you show that yes, it is possible. By calculation, you show that there is no other possibilities. Both of them are important. Is that understandable? Okay. Any questions? When the lesson ends? Okay, we have time. So what do you think about this problem? Can you do it for me, please? Okay, so now let us solve this problem. This is the last example for today. So here we have be a graph of order 18. So P is 18. Size is 25. So Q is 25. The little delta, the minimum degree is 1. The maximum degree, capital delta, is 5. G contains 6 vertices, each of degree 1. So let me just list all the degrees here. 1, 1, 1. So 6 of them. 4 vertices, each of degree 2. So I have 2, 2, 2, and 2. And then I do not have any. It is written that it does not contain any vertices of degree 3, but it determined the number of vertices of degree 4. Okay, so we don't know how many degree 4 vertices are there. So I would say that, okay, 4, 4. I don't know the number of them. Let me call m of them. But because delta is given to be 5, it means that at least there should be 1 degree 5 vertex, yes? But we don't know the number of them, so let us write 5, 5, up to 5n times. So this would be the generic sequence of the degrees of the vertices of this graph. On the other hand, we know that sigma, the total degree, if I add the degrees, it becomes 2 times the size. We just showed this formula. So this means that if I start adding these numbers, it should be 2 times the size, which would be 2 times 25. So, but if I add the degrees, I have 6 ones. So if I add them, it becomes 6. I have 4 twos. If I add them, it becomes 8. And then I have m fours. If I add them, it becomes 4m. And then I have n fives. When I add them, it becomes 5n. On the right-hand side, I will have 2 times 25, which is 50, yes? And now you see that 6 plus 8 is 14. I move it to the other side, so this means that I have 4n plus 5n equals to 36. This is one equation, but of course there are two unknowns in this problem, and one piece of information in general is not enough to calculate two pieces of information. But of course, on the other hand, if I ask you how many vertices you see in total, you say that I see 6 vertices here, 4 here, so up to here 10. And I see m of them here, n of them here. So it becomes 10 plus m plus n. So this would be the total number of vertices. But on the other hand, total number of vertices is defined is what we call the order, and order is given to be 18. So then this gives me that m plus n is equal to 8. This is another piece of information. So I put them together and I've solved this system. 4m plus 5n is equal to 36, and m plus n is equal to 8. So if you solve this system, you will get m equals to n equals to 4. So what is wanted in the problem? The problem asks you how many vertices of degree 4 are there. So it means that problem is asking you about m. So the answer would be 4 of them. But let us see if we can draw a graph for this. So here I have 18 points. So of course this is not demanded in the problem, but this is just an extra exercise that we want to do together. So here I have 18 points. So let me draw them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yes? And now I will try to draw a graph. Usually this might be a little bit challenging if you want to draw such a graph, but let me see what can I do. Here I have 4 degree 2. So let me try to do it in this way. So I would say, let me connect this to this, connect this to this to this one, and finally this to that one. So here at least I have 2, 2, 2, and 2. So yes, I have 4 degree 2 vertices. And then I want to have 6 ones. So let me concentrate here. So this is a discrete one. So for example here, hopefully, I don't know if this is going to work or not, but I will try to see how it works. So 1, 1, 1, 1, 1, 1. So it means that if this is going to work, I am not allowed to attach any other edges to these things because this will spoil the degree. So now I want to work here. According to my calculations, there should be 4 degree 4 and 4 degree 5 vertices. So how can we do that? So for example, let me concentrate here, one of them. So for example, let me concentrate, here. I connect it to this one. I want to make this one 5. So this one and that one. Okay, so far 4. And then one more, it becomes 5. So here, this is 5. Yes. So let me make this one also 5. So I will connect it to this one, and I will connect this to this one. I will connect this to this one as well. So 1, 2, 3, 4. I will connect this to this one as well. Okay, so this will give me another 5 till now. Okay, so now what I do, okay, let me make these two 5 again. So how, for example, I will take this one and 1, 2, 3, 4. So yes, I will connect this to this. I will connect this to this. I will connect this to this. And I will connect this to this one. I also connect this to this one. I'm not saying that this is the best way, but I'm trying to see if it works. So 1, 2, 3, 4, 5. So now this is also of degree 5. But now, how should I make it degree 5 here? So I will connect this to this one. I will also connect this to this one. I will also connect this to this one. And I will connect this to that one as well. I think it is done, hopefully, if I'm right. So this is 1, 2, 3, 4, 5. So that is 5. And then if I ask you what is the order here, you see 1, 2, 3, 4. So the order here is 4. The degree 4. Here is the degree 4. The degree here is also 4. And the degree here is also 4. So yeah, it's not that beautiful, but at least this is one possibility of drawing such a graph. So at least we showed that such a graph exists. Okay, so thank you for being with me. I will upload this video as usual onto YouTube channel, and you will get a link for downloading this PDF file below that video. Until the next session, be safe and goodbye. Thank you.